So let me share my screen. I can kind of show that off just because I think it would be a good example of one. If you're trying to look for one, you can probably find it. And so the example here, I don't know what that was doing. You should be able to see my screen. Let me know if you can't. So for example, a template pattern would look something like this. You would have like some kind of well-defined kind of algorithm or structure, and then you're going to slot in functions into each one depending upon some circumstances. So for example, you could have a movement function that you swap in, an interaction function that you swap in, and so on. And the idea is that therefore you can mix and match them. So you could create a spider that moves like a zombie, for example, right? And so if you're going to do this, the important thing is that these are passed into the constructor. You can have default values for them, which basically means you can just like set them within the constructor, but they should be passed into the constructor and set within the constructor. And typically they don't change. If they change, they're more of a strategy pattern, but so that could be a way you kind of get around it. If you needed like an extra pattern very quickly, is to kind of like separate the movement logic out into different like functions and then treat it as like a template pattern. Now, typically I would want to see multiple of these, but you can probably get away with it if you just have like one example. But like typically how we do these kind of patterns is that, I don't know, say 3 marks is for the pattern. That's a bullshit number. The real answer could be something less than that. If 3 marks are for the template pattern or for patterns in general, then you probably could get like 1.5 marks by having like around 1 to 2. But to get to kind of the rest of the marks, you would probably need to get patterns that are more well done. So you could probably kind of get away with one that's kind of a bit on the edge of kind of pushing what really is a pattern. For example, if you use state pattern for a Boolean, you had like a state pattern for the switches, for example. Like they're not really a state pattern. It's just like on and off, right? If you did this, then you'd kind of be stretching the truth a bit, and you'd be somewhere between 2.5 and 3 if the rest of your patterns were fine, right? Most likely 3 if you implemented it well. But if you implemented them less well, or they're clunky, or they're not really suitable, and that's happened a few times, your marks are basically can go kind of down from that point, depending on how many kind of infractions you have. I guess you could kind of feel it that way. It's not so much like negative marking; it's more just like we're kinder if there's fewer mistakes. Um, anyway, so that's kind of the tip for that thing. But let's go through these little examples here and kind of look at what you could use. So, for example, if you were sorting a collection of records in different orders. So, for example, sorting it by the name of the record or by the title of the oh, I guess the same thing. The name of the record, the artist, the duration, how many likes it has, I guess, or something weird like that. I mean, this is kind of like, I guess, music records in my head, but they could really be like generic records. So it could be kind of like it's just some data record. So I don't know, like a review, I guess. You could be sorting reviews for like a show or something. Um, and so if you're sorting those, what kind of pattern could you use to abstract the concept of the sort? Yep. What would the strategy be used for? So yeah, you could abstract the sorting algorithm itself. Um, Probably not too useful. But yeah, the what order you sort in is kind of the big one. Like if, for example, if you think about it, I guess you don't really have to sort in assignment one. I removed that. But typically in assignment one, you have to like sort all your lists. But I was like, that's stupid. It's so annoying to do it. And the way you would typically sort it is you would like call this kind of like sort function, and then you would like pass in a comparator, or something to compare by. And so you would say something like, let me just do it this way. You'd say like, hey, I want to sort this list, and my comparator comparing with something like this. you do something like this, and you'd say, okay, I want to compare by my satellite ID. And this would therefore compare all satellites based upon their ID, right? And so what's happening here is that this is like your strategy pattern, right? It's your strategy of what you're comparing by. So you can say, okay, compare by the ID, and then compare by, I don't know, the angle or position. This syntax is probably like 80% correct. I don't. Oh, this is definitely not dot. This is definitely just going to be like dot, like this. Anyway, but like it's there could be like this could be something called like order by or something. I would have to like when I'm writing it, I would figure it out. But you know, roughly something like this. And so that is that you're giving it some kind of key lookup that you're looking up, and then you're kind of this is like a almost kind of like a decorator. Have you covered decorators yet? Let's see. I thought you did, but it could be that decorators are later. Yeah, decorators are week 7, so you're covering them this week, but probably you haven't covered it yet. In 1531? Interesting. But yeah, so the way this works is this is what we call streams, and so streams are actually a classical case of decorators, funnily enough. And you'll probably see that a bit next week with the lab. Basically, next week's lab is kind of like build your own stream, kind of, I guess. And the rough way it kind of works is if you're kind of abstracting out a stream, what you want to do is you almost want to like kind of have streams composed of other streams. So you have this kind of like nesting relationship. So for example, inside your inner stream here, you may have like just like all your satellites. So for example, right? So this is your inner stream. And so this is just a like an iterator that just loops through all the satellites. And then you get, say, for example, you want to filter them based upon some condition. Maybe like the angle 2 degrees, sure, is greater than 180 or something. Greater than equal 180. So this is like your second layer. And so what it's going to do is it's going to grab all the inside records of this, and for each one, it's going to compare it. And then it's going to check if it matches this condition. And if it matches this condition, it will let it bubble through. And if it doesn't, it won't. So you kind of get this, like, it's literally a decorator, like this nesting. And so this then buys basically the same kind of idea here. And so what's going to happen is it's going to, like, create a new comparator, right? And so it's going to create, like, a new kind of class. I guess then I'll just write it here. And this new class is going to be, like, comparator, maybe like a binary comparator or something funky like that. And so what it would do is it would have 2 ones inside of it. It would have like A and B. Right? And then this comparator, when you ask it to compare 2 items, you know, for example, like item 1 and item 2, what it's going to do is it's going to use A. So it's going to basically go, hey, check if given A, you know, compare 1 to, I guess I will call them like, I just don't want to use A and B again. I guess we'll call them like alpha beta. Sure. Terrible naming, but good enough. So these are like alpha beta. These are like your 2 items that you're comparing. So you're trying to like check whether or not these items are equal in some way. So if you're comparing alpha beta, and if these results is equal to 0, then therefore what that means is that these values are the exact same thing. And in which case you're just going to return the comparison of the second one, right? Otherwise, you would return a.compare. Now, you'd probably write this so that you wouldn't call the function twice, but like, you know, it's kind of doesn't really matter for this simple example here. And so the way this works, right, is if you, for example, have like a list of students. Oh my God, I cannot write today. Students. And you have a list of students which have like ZIDs and have like, I don't know, favorite course. And so, for example, you could put like your ZID there. Let's just kind of do that. And then you would put your favorite course. I don't know, maybe it's like ciphers, for example, or I don't know, forensics. or something like that, then what you could do is you could sort by students based upon their favorite course, then their ZID. And so, for example, if you also had another student that also liked ciphers, I'm just going to keep the full stop. No, I'm not. Okay, it's going to know me. Okay, there we go. And so if you were going to compare these two, what would happen is the A comparison would compare by the course, and the B comparison would compare by the ZID. And so when it goes through, it's going to go, okay, compare ciphers to forensics. Ciphers is before forensics, so keep this order. So it's going to keep this order. This is the same. And this is presuming like a bubble sort, by the way. Obviously, it's probably not going to use bubble sort. Probably going to use some kind of block sort is my guess. Like a block sort's like a fancy merge sort. But it could be using something a little bit different. And then if it compared forensics to ciphers here, this would be a swap, in your kind of bubble sort case. So these two would swap. And then it would compare again by looping again through because, bubble sort, and would compare this cipher with the now moved cipher. Compare the ZIDs, this ZID is before this ZID, therefore it would keep the same order. So you would end up with 1, 2, 3. And so that's basically kind of how these kind of comparison functions work, is that you're kind of almost able to like abstract this kind of almost compositional relationship. So it's kind of this like weird mix between composite and decorator, which is kind of like funky, right? And the basically, I guess the distinction between a composite and a decorator is the intention more so than the code, because the code's pretty similar. With composite, the big kind of thing you're aiming for is you're trying to treat like an array of items as equivalent to the item itself. So for example, if you have like an array of Boolean conditions, right? You're trying to treat this as equal to a Boolean itself based upon some kind of reduction rule. So reduction is this kind of concept where you kind of grab like an array of items and you reduce it down to like a single value. And so, for example, a simple reduction could just be like the and, function, which is like, hey, I'm going to take in a Boolean and another Boolean. Jeez Louise. And I'm going to return you a Boolean, right? Holy cow. I am so bad at typing today. And so this would just be like, A and B basically. Yeah, kind of a self-referential definition here, I guess, but it's fine. And so, for example, if you have like a array of Boolean values and you're trying to say, okay, this is identical as this, addition is a reducer, yes. A reducer basically doesn't have to operate over an array, but typically operates over an array and just reduces that array down to a singular value. So all you typically need is like a starting value, like 0, and then some function that takes the accumulated value and some kind of current value. Now, it doesn't have to reduce it down to a single value, though. Like, it could do other things that are a little bit more funky, but that's typically its use case. So, for example, the addition here would be like, the function that you're using would just be the add function. So you would just see like accumulator, which is like your current accumulated value, and your current value, and you'll just do like addition of those two, right? Let's just erase this and replace this with a line, right? And that's kind of what you'd be writing here. Yeah. And so the same kind of thing here. So the idea of this is that you're kind of able to reduce something. I don't really know why I was talking about reduction. I'm sure it's relevant. Oh, composition. Yes, the whole point of composition is that you're trying to treat them as the same thing. And so what that means is that you can kind of look at like an expression, which is like very complicated. For example, it's an AND relationship up here, and then there's an OR relationship down here, and maybe this is like 3, and then each of these are like leaf nodes. And Z prime. I ran out of symbols. Let's just use a funky symbol for this one. That's not how you draw an alpha. And so if you kind of have this kind of weird structure, you're able to treat this as almost as if it's kind of like identical, or like, I don't really want to use the word identical, but almost like as if it behaves the same as just like the singular value alpha, right? And so it's almost like, or I guess I won't use alpha again. I'll use like beta or something, just like a different kind of value. So you're trying to like treat leaf nodes the same as like if they're non-leaf nodes, as if they actually contain like this hierarchy. And so, but with decorator pattern, you don't really care so much about this kind of relationship between the two. And it's more just about like modifying the behavior of the inner object, which could be multiple inner objects. Keep that in mind. But it's more about trying to modify their behavior in some way. So, for example, you're trying to decorate something. So, I don't know, let's say you have like a really nice outfit, right? You know, my awful drawing skills can come into handy here. And I don't know why I'm drawing something really, like, but sure, we can draw something for the example. It's a penguin. We have this like penguin here with legs. I I don't know. And if it wants to like attach this like cute little pin on like its, I don't know, its fur, I guess, or its penguin jacket, then that would be like a decorator that's attaching on top of it, right? And that may like add some appeal value, I guess, if you're trying to gamify it. So this could make the penguin very, very appealing to its peers. I don't know. And so this penguin could become very popular because it has this badge. And so the point is you're kind of augmenting something, you're boosting something, or you're kind of decorating something, you're kind of wrapping around something and adding unique kind of behavior. So I talked about this like a little bit last week with like file systems, so with zipped files and the assignment. So the zip file itself could be like a decorator that sits on top of a normal file, and it's kind of augmenting the behavior by zipping or unzipping the class, or unzipping the data rather. And so that's kind of the difference between the two, is that they kind of do the same thing, but one of them is more interested in trying to like, I mean, in a decorator, like it's the same, right? Like you treat the decorator object as if it was the same as just the inner object. Like, you know, if you have a stream here, these are treated exactly the same, basically, right? They're still both streams. And so it's kind of the same thing as composite, where you train the things as the same, but like the purpose is different. You know, for composite, you're not trying to augment the behavior. You're trying to group the behavior or reduce the behavior or kind of sum up the behavior to like a single value. Where with a decorator, you're almost trying to kind of build it on top of the behavior, extend it kind of. Anyway, that was a really long explanation for saying that was like relatively. I'm very distracted today, I guess. Modeling a file system, basically, there's a few ways you could do it. But it's probably going to be some kind of composite or decorator kind of relationship. You know, you have like folders, which are like your kind of composite nodes, and inside of that you have like, you know, symlinks, which are like, you know, kind of composites, even though they don't necessarily like compose of multiple objects. They're kind of just like a pointer to something, right? But you can kind of treat them the same, or I guess you could treat them as a decorator in that case. That, you know, that's where it kind of muddles the water a bit. Anyway, but let's say, for example, if you want to update a UI component when the state of a program changes, what could you use there to do that? What kind of design pattern could that be? Yeah, it kind of tricks you by using the word state. Yeah, probably observer. Like the big thing about UI is your UI should be really dumb. Like this is kind of a concept that we talk about a lot, I guess, when we talk about like any kind of user interface, whether or not it's games or not games. Your UI really shouldn't do anything like logical, and really should be pretty like straightforward and simple. And you can kind of see that with the project UI. It doesn't understand context. So you give it like an entity, and you're like, here's this entity, and it goes, this is an image. That's all it sees. It doesn't really see anything more, right? It doesn't go, oh, this is a player. This is special, right? I mean, the player is a bit special because if the player disappears, it will give you like a game over message. And that's kind of, I guess, probably something that shouldn't happen. It probably should be like abstracted a bit better. But regardless. And so when you kind of have this kind of stuff, you kind of want to keep things very simple. You know, for example, with the goals, it doesn't understand what goals are. It just kind of knows that, oh, okay, I will just render these goals, and if the goal is empty, then therefore there's no goals, and you've completed everything. You know, it's kind of simple. But even something like that, it's kind of you're adding behavior to things, and you probably could have like a boolean in the return value or the response that says, is the game complete? Is the player dead? What's the current state? You know, stuff like that. So you're kind of treating it as if it doesn't have to understand context or what things are. Anyway, so that's basically why we use observer there, because we just kind of want to tell it like small changes, like, hey, this value has changed, but so it doesn't actually have to like understand why or what it is. Parsing and evaluating arithmetic expressions. What do you think you could use for this one? So, for example, you have something like 1 plus 2 times, I don't know, 3 factorial divided by 9. Composite. Yeah, composite. I wouldn't say passing is composite at all. Like it's passing, if anything, is like a state pattern. But like I think they really mean evaluating here. A calculator pattern. I've not heard of that pattern. Oh, it's a joke. See, the problem is that there's so many patterns I can't tell which ones are actually joke because there are stupid ones. There's one called command pattern, which I thought I hate. Computer science love coming up with stupid names. The pass itself would probably be like there's two ways you can do modern passes, right? So modern passes use something called recursive descent. It's pretty common. It's pretty much like the way everyone does it nowadays. And the way recursive descent works is that you kind of pass it like it's like top down, but it's not really. It's like you recurse all the way down, and then you kind of build the table bottom up. So it's still kind of like bottom up, but like I'll kind of explain what I mean. So for example, if you have this expression up here, the way a recursive descent passer will look at this is it will read like a symbol at a time. So it will read, oh my god, it will read the symbol 1 here and go, okay, I want to read a number. But before it does that, it figures out what this is and goes, okay, this is a number, sure. But it doesn't even understand what it's looking for. So rather than trying to look at the symbols and understand what the context is, it first starts out like this kind of like very top level and then figures out whether or not the symbols correspond to that context. It's like the other way around. So you have like this top level expression and it goes, okay, I'm in an expression function. This is like a function, right? And it goes, what is the first symbol that I see given that I'm within this function? And it looks at it and goes, huh, it's a number. I can't do anything with that. So what I'm going to do is I'm going to do a big switch statement and check what the type of it is. And the switch statement will look something like this and will typically figure out the type. Now it will typically go, hey, is this a function? No, it's not. Is this an identifier? No, it's not. And we'll kind of break it down that way. But that's still not great. And so the way recursive descent works is it actually kind of does the opposite. And it goes, instead of trying to like figure out what the symbol is, it just does like a simple equals check. So it basically goes, for an expression, it's still pretty generic. So it probably would immediately default to the next level, which is like a conditional expression, unless you're having things like functions and stuff, where it could be a bit more funky. And a conditional expression is something like, for example, like or and, right? And due to precedence laws, it's probably going to process the or first. So it probably will do like an or expression first. And it will check whether or not the symbol is equal to or. But the problem with an or expression is it's like A or B, right? So it can't check if it's equal to an or yet. So it first has to pass the A. So what it will do is it will go, okay, for me to pass an A, inside of me must be a conditional expression that is an and. Right? So this is where it passes the and part of the conditional expression. Right? And then this will go, okay, so I'm going to be followed by a symbol that's like A, followed by and, followed by B, for example. So now I need to pass my A. So then it's going to go one level deeper. And then it's going to go into something like, for example, it's back to front, so I have to think of the right ordering. I think it would be addition next. And then it would be like, for example, addition / subtraction, And then you would have like your multiplication / your division. And I'm not doing like equality here. I'm just doing like these very simple things. And so it would kind of keep going all the way deeper each time, which is kind of insane. And then kind of goes all the way down until, but each of these are just like, for example, addition and subtraction is like A plus B, right? But again, before it looks for the plus, it needs to look for the A. So like that's what it's basically doing, is it's kind of going all the way down to it like reaches a point where it terminates and finds A. And then it looks for the next symbol and sees whether or not the next symbol is like a plus or a times or a divide. And then based on that, it will kind of continue a loop. And so in this case, it will kind of, and actually, will these be flipped? I got to think of precedence. So if I have like A or B plus 2, it will be like this, which means that'll be fine. If I have B times C plus D, it needs to do the it needs to do the addition first. Yeah, no, this is fine. Okay, so what it needs to do next is it needs to kind of go one level deeper, which is probably like the factorial here. You know, the kind of exclamation mark. And then it's going to go one level deeper, which is typically what we call your atom, right? And the atom is kind of like this lowest level. And this is basically kind of like your, I guess you would just call it like your numbers in your text. So for example, if you have like x times 2, right? The x here would be your atom. And so would the 2. And typically, the way you also express the atom is for manual parentheses as well. So manual parentheses would also count as an atom because it's like the highest precedence, right? It's the thing you want to handle first. So for example, it's going to go all the way down and find the 1 here. So what's going to happen is it's basically going to grab the 1 and say, okay, there's a 1. I'm going to have to build this table pretty big. So let me just do it to the right here. And it will be, I guess, here. It's probably enough room. And so it's going to find the 1 as the atom. It's then going to go back and say, okay, was there a factorial symbol after it? No. Was there a multiplication / division symbol after it? No. Was there addition symbol after it? Yes. So then therefore it's going to register the plus. And then it's going to go back down again to register the B. And so this time it's going to handle the B side. So basically it's kind of like adding a fake parentheses here. And so you can kind of see how it's respecting the precedence laws by doing that. And so with this multiplication division, what it's going to do is it's again going to do the same thing where it tries to find A again, right? So it's going to go all the way down and find 2. I guess 2 will be like here. And then it's going to go all the way back up again to find the multiplication. And then it's going to create the multiplication symbol. And then it's going to go all the way right again to find the B. But this time, when it reaches the atom, it's going to find the fact that it's an open parentheses, or parentheses. So then what it's going to do is this atom is then going to go all the way back and call an expression within itself. So then it's going to start the whole process again for this thing inside of it, which is again going to go, all the way down. So I guess I can kind of build the parentheses here at least. So this is like a parentheses. Typically, we don't include this within the AST, but that's fine. And the AST is just like the syntax tree that this produces, this kind of composite relationship. And so within this, you can have another expression, which is just going to be a single line. And so you're going to have the factorial, which is going to be the 3 here. And we would typically call this a unary function because it's, a single argument. And I guess you would see something that looks like this. And then what you'd do is you would end up with I'm going to do a division symbol here. A division symbol that would then split off into your factorial and your 9. Right, and then these would factor all the way up. And then finally, you can connect this times with the plus, right? After that all returns. So you're kind of using the stack to kind of build this tree. And it's almost like it kind of builds it bottom up. But not really, because it doesn't look at the symbols from a bottom-up perspective. It looks at the symbols from like a top-down perspective, which is why it's called recursive descent. You're like descending downwards, and then you're kind of recursing all the way back up. And it's also kind of recursive, which is why it's called recursive descent, right? Because you kind of have this like recursive relationship here with like the atom recursing back for the expression. And so this is the way that typically you pass things. And so this is very common nowadays. This is extremely popular. It's pretty much most modern compilers use this method, but it's not the only way to do it. And so the other way you can do it is via a state pattern. And this was very common in like the 90s. And if you use there's certain stuff called auto-generated passes. I know there's a fancier word for them, but I don't remember it. No one really likes them anymore. I really hate auto-generated passes. Like part of the fun of writing it is like writing it. And they give really bad errors, which is why no one really likes them. But basically auto-generated passes, you kind of give it what we call an EBNF, which is kind of like a language structure. Do I have an EBNF? probably, I've got a very simple EBNF probably somewhere. If anything, it'd be here. Oh my God, I do. Look at that. So this is what an EBNF typically looks like. And so, for example, you'd have your program, which consists of a series of expressions. Then each expression is like a logical OR expression. And then your logical OR expression looks like this. And logical OR is a logical AND, which is a comparison, which is an additive, which is a multiplicative, which is a unary, right? And so you can see how it kind of like has the same relationship that I was just talking about, like with the nesting. And that's basically like the structure that you get. And so what it does is it picks this up and then builds a state pattern to pass it. This is a huge distraction today. Anyway, and so it's actually really interesting with how they work, but they're kind of terrible. Anyway, recursive descent pass is actually really easy to write once you've written one or two, which is nice. But yeah, so that's basically the difference between like a recursive descent and state pattern, what you're using them for. But the big point of all of this is that in the end, what does this look like? Right? This is a composite pattern, and that's basically what you use it as. And so there's kind of two ways you can structure abstract syntax trees. And the first way is a nightmare way. And what you do is you basically structure it like this. So in this case, it would be... I'm not going to do the full thing because it would take me forever to do the full thing. But you would have like an expression, which would inside of it have a conditional OR expression, which inside of it would have a conditional AND expression, which inside of it would have a add and sub, which actually would have a value. You know, you'd have your add, and then inside of this would have like 1, which actually by itself wouldn't be 1. This would be a multiplication, which would, inside of it would be a factorial, which inside of it would be an atom, which inside of it would probably be 1. Right? You can see how crazy this gets, and that's just for plus, and it's just going to be the same. You kind of get these like really big trees, and they're like really big pains to pass and handle. And so the point of the composite pattern here is it lets us treat each of these nodes as if it kind of still has this kind of context of like the full state tree, but we can still just treat it as the number 1. So for example, if we want to like resolve this, it's very easy for us to just say, check your left node. Oh, it's the number 1. Okay, sweet. And so this is like what we would probably call like, I guess, a denormalized form, because it doesn't have like the typical structure that you're passing it as. And it doesn't match the grammar. So this no longer matches the grammar, but it still semantically is the same and is what we do. Yeah, anyway, that's a big distraction. So that was one point. And the final one is observer, just so hopefully don't get too distracted. And the observer here is just this final point, which is the brightness of a screen. So you're kind of having some reaction. Now, typically, again, I don't know. If you ask like a electrical engineer whether or not they would use an observer for this, they'd probably laugh at you. You probably wouldn't use an observer. You'd probably use a polling system. Maybe you could like link it up to some kind of like how the OS will treat it is, even if you have an observer, the OS will still be polling it. Because typically how these things work is that you have some kind of like light sensor, for example. You know, and this light sensor is like sending some kind of signal. And typically the signal is like a voltage, which is like a measurement of kind of like, yeah, I guess I'm going to do that. So just sending like a measurement down this kind of wire into some kind of like voltage reader typically. And as the voltage increases, you know, that could mean like there's more light. And typically these work via something called electrovoltaic cells, which is basically when light hits it, it turns it into electricity. Basically how solar panels work. So basically you would have a solar panel, right? It's effectively how light sensors work. Is a very terrible solar panel. Then that sends some kind of signal to say, yes, I've got, you know, this much charge, and you kind of relate that to like a light level kind of. And then what your system will do is it would kind of take this constant signal and then convert it into like a series of updates. So it would almost be like it's kind of polling it or constantly checking it, but you would kind of do that separately, and then that would eventually send like an observing update to your application. Anyway, let's write a calculator pretty quickly. I was going to do a parser, but I think I kind of explained all I really wanted to do about a parser, where you kind of like abstracted down. But if we find some time, we can do it. We don't need to do that. Let's go here. And let me write classes. Fun. Okay, so I was like, at least I was hoping there's structure, but I forgot I did not add structure to this because there's no structure in the one given to us. So let's just write a very simple kind of starting thing. So we're just going to write some kind of expression class. I'm just going to mark as an interface. Now, it will get very funky if I do it this way. So let's actually just add like a calculator object here. Add the source to the Java source path. Yep. Thank you. And now it actually wants a package. Why do I keep doing that? Inside this interface for this expression, this is basically going to manage both our composite ones and our non-composite ones. And so the easiest way to do this is probably just to have some kind of like evaluate function is typically what I like doing. Now, the funny thing about this is that like this is always going to evaluate to like a double result, but you probably would have this as being more generic. It'd be like some kind of like atom that it'd evaluate, but anyway, it's fine. So you're saying, hey, this expression needs to evaluate to like a result. Okay, and so for example, the evaluation can just be a double here. We don't have to go crazy, and let's just create a bunch of classes. A good one would be addition expression, which would just be a class, and this would just implement expression. Now, I'm going to show you another way to do this that's really, really cool. And the other way to do it is using enums, and it's really, really funky, and it's really nice. And there was a past exam question that people really didn't like that basically kind of was this in a bit of a harder way. We're not going to give it to you again. So you don't really have to worry about solving it. But it was actually a really cool question. It had a really, really nice solution. And yeah, it was really funny seeing people go, like, oh, I wrote like 200 lines for that solution when the solution was like 20 lines. It kind of hurts sometimes here when you have like these small things, simple things. And so that's actually a recommendation. I'll talk about exams later on. But one of the big things that people found, I think, last time is that, I mean, the exam will be easier this time around. But, well, it depends. But probably like it won't be as, I don't know. I don't want to say it will be easier, and because I probably won't be designing it. But it should, I would expect it to maybe be easier. But the thing about the exam is that a lot of people found that like time pressure was hard because they had to think of like patterns and stuff really fast. But what you'll often find is a lot of the examples you get given are examples that exist within the course through like labs or tutes. But you don't have to remember them. You just have to practice a few of them. Like once you do like one or two, you kind of get it. So a classical example is I don't know, like the expression one is very commonly used, right? Having some kind of expression evaluate. That's basically just composite every time, right? But if I say, okay, hey, you've walked into a shop and you're gonna make an ice cream cone. And so ice cream cone is comprised of ice cream that sits in a cone, and you can put sprinkles, you can put caramel, you can put, I don't know what people put in cones. Stuff. I don't know, like depends, I guess, where you live. Maybe if you're in California, you can put certain stuff on it or whatever. And you know, maybe you put like, I don't know, chocolate. You know, the freezy stuff that I had as a kid. It was like you put it on the ice cream and like freezes up and like makes it like it goes like hard and it's like kind of chocolatey. Anyway, and so you kind of have all these like various different toppings. I don't know, maybe put like jelly beans or something in there. And once you've done that, you kind of have this ice cream cone. Now, the way you structure that, yeah, magic chocolate, that's the one. That I remember that stuff. That stuff was good childhood memory. And so when you have that kind of structure, yeah, that stuff was good. It was like it was legitimately like I feel like it was probably like terrible chocolate, but just the fact that like like was magical in like some kind of way just made it like freaking fantastic. Anyway, so yes, you kind of put your magic chocolate or whatever else you want, like the sprinkles on top, and a lot of people go, "Oh, I don't know, really know what that is," but you got to think about like, well, what are you doing to the stuff? Well, for each layer, you're kind of augmenting it. And that price change is going to happen. So, for example, maybe sprinkles makes everything 2 times more expensive. Maybe magic chocolate is free. And so what that means is you're augmenting the price. And so the recognition there is that goes, oh, that's decorator pattern. And a lot of people looked at that and went, it's strategy pattern. It's like, well, is it? Not really, because if you're like doubling the price, but only if the inner layer is chocolate, or sprinkles can only be added on top of if there's no chocolate in between. Those kind of like restrictions kind of inherently make it layered. Anyway, I guess I would just have like expression A B, and then this could just like have like a public add expression. Oh, I can be funky here. Let's just do it this way. Constructors, funky. And then we need a compute function. And this compute function will just evaluate. And we'll just return a dot evaluate plus b dot evaluate. And I can write a very simple test for that. And I never remember the syntax for tests in Java because it's so obscure and has all these like random symbols that don't really mean much. I don't have to put anything in the class. Nice. Okay, let's just do like test simple. It's terrible testing, but it's fine. That's the wrong test. Jupyter. There we go. And so we can just do something as simple as like create like an expression e should equal e dot I don't know, like a new e rather. And this add expression will take in like 2 arguments, maybe like another add expression, like 1, 2. You also need a leaf node, like I don't know, number. Number is probably not a good name for this. Like atom. We got atom. We got atom because it's like the smallest thing. Modern software development takes like 30 seconds to goddamn rename a file. Why? Why does this take so long to rename a file? Cancel. I can rename the file myself. Thank God. Oh my God. You're like renaming a file and you're just renaming the class that matches that file. Anyway, it's just ridiculous. Value. And this is also an expression in some kind of weird way. Come on. This code drives me crazy, man. Yeah, that's what I meant. And so basically that's it. So then we kind of have this kind of atom node, and so therefore we can create like 1, 2 by saying like new atom 1, new atom 2. And then this could also be like a new atom. Okay. And this should be 7, which I should do in an assert. And I should do it this way. Okay, apparently that assert equals is not. Oh my God, it's the other one, isn't it? Okay, chill out. API is it like assertions? The wonderful joys of like dealing with Java's need to deprecate things and then not define like actually useful equivalents. Yeah, that's the one I'm thinking of. Thank you. But yeah, I found it anyway. It deprecates like the old stuff, but still keeps it around, and so it's just so easy to import it. It's, I don't know, my daily rant about Java annoyance. But anyways, this works. Yeah, okay, great. So we have some kind of atom expression here. We could make a very easy multiplication expression. I'm a bit wary of time, so I'm going to go pretty quick. But you notice like a really common pattern, which is that I'm writing so much goddamn code just to do this. Like, this is driving me crazy. So the first step is to go, okay, well, that's too insane. I'm going to create a binary expression because I want to be somewhat sane with my life. And this binary expression is going to, by the way, in exams and stuff, you don't have to do it this way. It just will take more time if you don't, typically. It's like, this stuff is pretty like, implements. This stuff is like pretty okay. Like, you can implement stuff most ways. If you do this like long way, you'll still get all the marks. It's just like trying to teach you some faster ways to do things. So this binary expression, what it's going to do is it's going to take in a function that's like, hey, this is how this binary expression evaluates. And typically I make this private because I don't want to just like randomly pass in functions to this. I don't know, it just feels weird. And this is going to have like a by producer, no, a by function, yes. And this by function is going to take 2 arguments and return a result. And so if I do like, I don't know, func, sure, func, and don't do underscores, this dot func equals func. Then what I can do is in the evaluate function just says, okay, sweet, this is my evaluation, and then also I want like 2 expressions which are within me, like AB, and expression G's Louise, AB, this dot A equals A, this dot B equals B. And then we would return a func.evaluate or apply AB. Now I need to give this arguments, so let me just do it now. So this is double, 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 trouble. And there's our evaluation. So now what we can do is we can now apply this, which means that these need to also be evaluated. And now we have a generic function that we can use for anything. And so that we can add this very nice binary expression. And this is, by the way, typically probably how you'd represent it within like a game. Typically, you'd have like not a game, like a parser. You'd actually have like a binary expression class, which would have like this different type of binary expressions within it. Because there's no real point like kind of generalizing it into individual classes. That's insane. Like to kind of come back to this, I'm pretty sure this has like an actual example. It's quite old. Immediately sus that it's called that. Is it this one? I don't know. I don't remember what anything is. But if I look at like my AST, yeah, like I have all my operators here rather than these being different classes, just like an enum of all the choices. Anywho, so then you have like some kind of binary expression here, and this could be like add, for example. And so this would have like expression A, expression B, and this would like return a new binary expression, which would be like given A and given B, add them. Now there's probably already a function that exists. Maybe. If it's not under here, it'd probably be under functional. If there's no add function. Sum. It's called sum. Sure. I guess sum is an okay word to use there. And so therefore you can sum the two, but then you could also maybe like multiply. I don't know if this one will actually have like any function relevant for this. Like, where's sum located? Is there stuff around sum? There's like min, max. Yeah, it doesn't look like it, but there's probably one under functional. I don't know. I'm not gonna look for it. I'm just gonna write it myself. There you go. And you can figure it out, but it doesn't want to for some reason. Maybe. Oh, it just doesn't like me using A and B again. Okay. Sure. XY. X times Y. Yay. Okay, awesome. Oh, that could be true. Product. Nope, it's not product. Maybe it is. Nope, no product. Okay. Oh, well, that's fine. It's okay. Doesn't really matter. And so this is like the next step. And so now what you have is you have a slightly nicer test. And so rather than looking like kind of a bunch of news, you wouldn't even have like the add expression, obviously, but you just have like binary expression dot add, and this would be like new atom. Like even atom would have like an atom dot int, for example, and like an atom dot double probably. Anyway. Wait, this is within an int expression, isn't it? So binary expression dot add this new atom for like this. And this is like test 2, I don't know, test 1. Very bad names for tests, but let's just go kind of fast with this because time. I do indeed want to press this button. Can you run the test for me? The test will pass. I think it's not too much of a stretch to imagine the test will pass. I don't think we need to like press the run button. Anyway, I don't know why it's not running it. I'm sure it's just an output window. I just don't want to. Java. I just don't want to deal with that. Okay, so then next we're gonna have like expression, a binary expression, enum, which is like an enum variant. And this is like a really cool way of doing it. So what you do is you have like add, you have like multiply, and so on. And then you can have like your by consumer down here. So by function. By function. And this by function is going to be called func. And then you have like some kind of, I guess, I wonder if enums can implement things. I presume not. It can. Nice. Okay, that's actually pretty nice. This could turn like, oh, I guess I don't really want it to evaluate expressions because I don't really want it to store things. Anyway, so this can just have like a public double eval, and then it would have like 2 arguments. Which are like, I guess, the 2 doubles. Right? And then within this, it would just go like return func.eval, or apply, sorry. And then all you need to do is you just need to find some kind of constructor to set this. So it has to be a private constructor, because you can't do public constructors with enums. And then this would take in the by func. And we'd set the by func. And then now this is going to complain. And so then this becomes a sum. And like this. And so now what you have is you have all your expressions and all your evaluations hidden away in these very nice classes. And so then what you can do is you can go and change how your binary expression works. I'm going to change this class name. Binary operators is like an infinitely better name for that. And then what this does, this just takes in a binary operator. This seems stupid, but now this can become public. And now, it really wants me to operate. Wait, what? Why is it going crazy? Save it. I don't know. Okay, there we go. And so now what that means is if we want to add new operators, we just add them here. So we no longer have to change this expression class. It's only one class that we're changing. And then this just becomes a new binary expression, and we just give it binary operators dot add. And this also becomes a new binary expression with binary operators dot add. Which again won't run. So you can kind of see how you start off with something simple where it's like very distributed and you have like a ton of classes. And then what you do is you're kind of transitioning it into this like middle stage where you have like, as we saw like back here, where we had all these kind of static functions here. This is what we basically call a factory, effectively, right? These kind of static functions like this could be think of as like factory methods. And so what you could have is you could have an expression factory, and that expression factory would have all the static functions for every single expression within it. And so that could kind of be generic, right? That's a valid way of doing things. And then what you do is you would then kind of go to this like kind of almost like final stage, which is also valid, where you kind of go a bit more functional. This is a bit more of a functional style. Doing it this way, it's kind of similar to what we call an ADT or a algebraic data type. So not an abstract data type, but an algebraic data type, where basically you have enums with like that can hold values. In this case, these values are static, so it's not really the same, but at least they're holding context. And so the idea is that like you're kind of binding this context between the two. And so what that means is it becomes a bit easier. You're kind of separating the concept of how a binary expression operates to how the operators work. So like the list of operators. So it's very easy for me to add new ones. I just add a single line. Right? Compared to a whole new class. Maybe that makes sense? Hopefully. It's very funky, very, very useful for things like the project, for example. I think, or maybe not so much for the project, but can be very useful in time pressure to kind of write these very nice enum classes that do like a lot of your logic for you. Is that everything? Yeah. So in the end, I actually did kind of change back to kind of doing a bit more of a functional, a strategy pattern, not a strategy pattern, a factory pattern for it. And so on. Yeah. Anyway, before we finish this up and jump on to the second part of this, which is basically going to be me going to each group and spending a bit of time with you, giving you some kind of feedback on your project and doing stuff like that, and marking your labs. So obviously we've got quite a few labs to mark. So